Hello, everybody. I'm pleased to introduce the speaker of today, who is Professor Adamo from Stockholm University. Well, Angela is one of the main worldwide recognized expert in the field of star clusters, both at low redshift and at high redshift. As you probably see in a few minutes, she is the leading author of, in the past few years, of very important results obtained mostly with the James Webb Space Telescope. She will show some very impressive and beautiful images of the distant universe collected with the James Webb about the primordial star cluster. And okay, some historical introduction on Angela.
Historical makes me look quite
old. She's also quite old, as you see. No, she comes from Sicily. She comes from Sicily, from a small village in the middle of Sicily. Long time ago, she came to Padova. And she graduated here in Padova, of course, with the honors, maximum votes. She graduated before me. And yes, then she moved to, I mean, this is, I think, is also a kind of opportunity for students in the sense that you have the opportunity to talk with her. Maybe she will share the opportunity, she will share the point of view of a scientist who did a career similar to some of you, but now she is working as an important astronomer abroad. And okay, then she moved to Sweden, to Stockholm. She did her PhD there. She spent some time at Max Planck in Heidelberg, and she's back now in Stockholm, where she's one of these big professors. She's director of bachelor and master degrees, many other duties. She is principal investigator of huge amount of time with the Hubble, James Webb, and other important facilities. Exactly. And yeah, she's mom of two beautiful children.
Okay, thank you, Antonio.
We will talk about private things later.
Okay. Good afternoon, everyone. Can you hear me? Okay, this is a very large room. Can you raise your hands if you have done even just an introductory course in astronomy? Okay, most of you, but not all of you. Okay, very good. I will try to explain most of the concept that I will mention. And if there is something that you don't understand, please raise your hands and ask a question. It's better like that you just go through all the talk and, you know, switch off your brain. So let's make this 45 minutes worth your time. And today I will talk about star clusters, and I will just introduce in one slide what they are. And I will show you how with the James Webb Space Telescope, actually we can study star cluster at all redshift. And when I will mention redshift, I mean like looking back in time into a younger universe and younger galaxies, okay? So now we are at redshift 0, and the local universe is redshift 0. And then when I will mention redshift 2, 6, 10, then we are really going back in time and see how galaxies looked like, where they were just primordial, you know, very young, forming not the first, we have not yet found the very first generation of stars, but quite very, very young galaxies, primordial. So this is a beautiful, it's better on my screen. Yes, better, sorry. Thanks. This is a beautiful view of the Milky Way from Chile, where we have some of the most powerful telescopes on the ground. And you see, essentially, one key ingredient is that we are in the disk of the Milky Way. And when we try to look at our Milky Way population, we see it just as in a slice, because we are sitting in the disk. And therefore, the view that we get of how stars form in our own galaxy, it's excellent. We can resolve the smallest details, but it's also very busy and crowded. We cannot really see the entire way that our disk is forming stars. And then we use different wavelengths. Now I know if you are a physicist, you are used to frequencies, but millimeter are very low frequencies, and optical going into UV, then it's like a higher energy and higher frequencies. So here we are looking at a region in our Milky Way which is gonna form stars. So this, we call it geomolecular clouds. It's dense gas which is emitting thermal emission, okay? It's like maybe a gas at 20 Kelvin, okay? And it's emitting because it's actually quite dense, and that means that it's collapsing, okay? And collapsing forms stars. And if we wait about 1 million years, what we will see, or 1 to 2 million years, a region like Westerlund 2, we are still in our Milky Way disk. And then look how beautiful it looks. There is this concentration of star, and there is this nebulae around, and it's emitting because it's warm, it's 10,000 Kelvin, but it's also dark here at the very edges. And these are the regions that are colder. We are looking at a region of 100 Kelvin, sorry. Now, this is a view provided by optical telescope. This is millimeter, but now we are reaching near infrared optical. And therefore, the dust here appears as a dark emission. But you will see in a couple of slides that with JWST, we can see it as actually bright emission, because JWST is more sensitive to the mid-infrared. If we wait still a couple of million years, all this gas will be gone. And then we find ourselves with the regions that we call star cluster. This is actually a beautiful example of the Pleiades, which we can see also with naked eyes from Earth. And then there are some very beautiful, very dense stellar systems. They are a globular cluster. And as you can see, these look also yellow in the optical. It means that the stars here are very old. They are much older than our own sun. So we are looking at systems that formed when the Milky Way, in the Milky Way progenitor, so before it became the disk that we know it is. So for the rest of the talk, I will talk about YSC. It means Young Star Cluster. So if it's not spelled out, you know what it is. Young Star Cluster is a compact stellar ensemble with size of 1 to 10 parsec. 1 parsec is the distance between us and the nearest star, okay? And that is filled with almost 1 million stars. These are star clusters, very dense stellar system, okay? And then they have stellar masses. So this is the total, how much mass there is in stars in this system. This is a 10 to the 3 solar masses object. This is a 10 to the 6 solar masses. So 1 million solar masses in roughly a few parsec size. And if they are like this object, they can survive very long. So this system has come through a long way. So it has formed maybe when the Milky Way was just a few 100 million years old. And it has survived and has reached us after a Hubble time. So one more concept about young star cluster. They are the places where most massive stars are forming, okay? So if you have done some basic thermodynamics course, you know that you cannot collapse an object if you reach the Eddington limit. So if radiation pressure contrasts gravity, you cannot then collapse further. And this limit gives you massive stars, which are a maximum, theoretically, of around 100 solar masses, 120. In this very dense region, this is R136 inside the 30 Doradus in the Large Magellanic Cloud. we find actually that there are very massive stars. So this mass of these stars, if the Eddington limit allows you to form 120 solar masses, here we have stars that are a factor of 2 or 3 more massive, okay? And this is really interesting because you can form such massive stars only when you have a dense young star cluster. And for those of you who have been doing a bit of atomic physics, we are looking here at spectra. So you see this is a flux unit, and this is wavelength again. And all these lines are absorption lines, are the fingerprints of the elements in the stars, okay? So in this cluster, there are stars that are not very massive, and the difference is here. This star doesn't have this emission line, helium-2, while very massive stars do. And what is telling us that there is a helium-2 or there is not helium-2? To produce helium-2, you need photons with energy above 54 electron volts. So you need really very high energy for energetic photons that you cannot create unless you have these very massive stars. So this is, again, important because it tells us that the energy that the stars, massive stars produce will feed back into the surroundings. And this is now the final concept. We already looked at Westerlund 2 in the initial slides. Now you are seeing the star cluster, and it's not by chance that the gas around the star cluster has this shape. The shape is produced because the feedback from the massive stars is pushing away the gas, is ionizing the gas, and is also dissolving, okay? So all the feedback, and there are different types of feedback, and in particular is UV radiation, which produce both photoionize the gas, but also produce pressure, thermal pressure. There are stellar winds, and this is due to the fact that massive stars can shred their envelopes, circumstellar envelopes, in very dense wind that produce shocks. And these circumstellar material are very enriched because they've already gone through the hydrogen burning, okay? So we see elements as nitrogen, for instance, around these very massive stars. And then there are supernova explosions. And these explosions produce a lot of not only luminosity, so that's how we discovered them, but actually most of their energy is produced as mechanical energy, kinetic energy, okay? So this is the Milky Way, but if we look at the nearby galaxy, this is one of my favorite, M83, it's just 5 megaparsec away, and we have a vantage point now. We are looking at face-on disks. And now we cannot resolve the details of single stars, but star clusters still pop up as bright regions, and we can actually now follow instantaneously all the phases. We see them forming, we see them producing feedback and affecting the interstellar medium of the galaxy, and then look, they stay bound in the disk for a certain time, so we can follow them in time in the disk. So this is some of the key concepts that you need to understand the rest of the talk. And my goal for today is to take you through a journey through our universe. This is a classic cartoon of how we see the universe formed. We see the Big Bang. We see the region after hydrogen recombines, the last scattering surface, the universe becomes dark and stays dark for quite a long while. But actually structures are collapsing, gravitational structures are collapsing, and gases are accreting in them. And primordial galaxies are forming. Here we see the first primordial galaxies. And then we see that they are creating bubbles. These are ionizing photons, energetic photons escaping from massive stars in this galaxy, reionizing the universe. And this process takes quite a long time, almost 1 gigayear. So we are here in these regions until the universe becomes transparent to ionizing radiation. And then we see, after this point, the galaxies are rapidly growing in mass to become the spiral galaxy or the massive galaxy that we see nowadays at redshift 0. So this journey will be done with the JWST Space Telescope data and also with James Webb Space Telescope data, okay? JWST, JWST will be what I will say. And I will show you how they both complement each other to show us exactly where stars are forming and how star clusters evolve in their galaxies. So the first part of the talk, I will focus on the emerging phase of star clusters. So this phase of cluster forming out of geomolecular clouds and emerging from these clouds and creating H2 region. And I call this the JWST revolution. Here you have, again, this is a spectrum in different units, but still flux, and the observed wavelengths. And you see this is far UV, and we are going to mid-infrared. And you see emission in the optical. This is what JWST, looking at this star cluster, will produce, okay? It shows the optical light, we see the stars, and we see the ionized gas. When we look at the same region with JWST, now the dark edges are bright because JWST is sensitive to infrared emission and allow us to see at the, for instance, these are called the PIH, I have to read it because it's too complicated to say, polycyclic aromatic hydrocarbons. These are molecules, giant molecules of carbon and hydrogen, or carbon, depends which one we are looking at. They live in the medium of our galaxy and become part of the dust that is created in galaxies. And that's why when they are excited, they become bright and emit. So we have this starless phase, our geomolecular clouds. And then if we wait for a certain time, stars are forming within them. And the feedback from these stars is ionizing the ISM and produce H2 region. So these are gas at 10,000 Kelvin with density of roughly 100 to 1,000 electron per cubic centimeter. And then around this H2 region, we see this light blue. This is what we call a photodissociation region. It's where a PIH, these complex molecules of carbon, get excited. And it's also the region where hydrogen, molecular hydrogen, H2, is warm. So it's not yet destroyed. And here, hydrogen, essentially, it's molecular and it's cold, okay? So it becomes like an onion, if you want to think of it. And then finally, this layer of dense cold gas disappears, and the H2 region becomes like a donut. So this is a bit the image we have looked at. And finally, we have this young star cluster that just moves away and stays in the disk of the galaxy. The key question that we can now address with the James Webb is how long it takes for a geomolecular cloud to become a star cluster. And this is not just because we are curious. We want to answer this question. It's actually really important to look at them because determining these timescales tell us the energy balance in the gas of the galaxy. So it regulates the star formation in the galaxy. Once this dense gas is gone, you cannot form any more planets. So to understand for how long how much time is available to form planets, you need to provide these time scales. And also simply by removing the dense gas, you are essentially killing star formation. So once the cloud is gone, the dense gas is gone, you will not form more stars. So this is a beautiful image of already a very old data set of just 3 years old. It's the FEAST data set. We proposed to observe with JWST at 5 galaxies in the nearby universe. And in particular, you see M51, the Whirlpool galaxies. These are observed with James Webb. It's a quite famous image. Is showing a medium which is really fragmented. And all the galaxies do that. Except for these two, it's even more impressive. These are dwarf galaxies. And the feedback from massive stars has blown the gas. So we really see this effect of outflow gas from galaxies. This is a bit more technical, but again, with the filters, so in astronomy, we use filters which provide signal at a specific wavelength. That's very powerful, because when you combine different filters, you can understand the energy and the composition of the physical object that you observe. So this is a work that a student in my group has recently published. And this is a star-forming region now, and the resolution is not as beautiful as when we were looking at the Milky Way. But each bright region here, you see, it's actually a star cluster. So this is a complex star-forming region. And you see in red are regions where stars are still embedded, while in yellow, in this figure, you see, are those that are emerging, and in blue are those that are out. And I invite you to focus mostly on these two together. So the red circle, for instance, are in both images. These are JWST images. But when we look at the optical JWST, they are dark. And this is because they are embedded under the dust of these giant molecular clouds. There is a connection to where we find embedded star cluster and emerged one. So the light blue dots are clusters that don't have gas anymore associated to them, so they are a bit older, while the red ones coincide with the dust lane in JWST. It's where stars are forming now. So Alex actually looked at 4 of the fifth target together, and this is now a JWST color diagram. So we use the filter to look at the properties, physical properties. When we plot a color diagram, they give us the age, for instance, of the object, okay? And what Alex found here is that the embedded star cluster are very red. Their color are positive in both indexes. This means that they are very embedded. And then there is this intermediate phase, and there is the optically bright phase. And you see, this is a model that doesn't have dust. The clusters should all be sitting along this evolutionary track, but they don't, because they are still associated with their dust. And here there is a lot of dust. Here it's less, and here it is gone. And we are now where we expect the color to be. Okay, so this is very important, because we have now the tool to find the different phases. We can estimate how long it takes. And I invite you also to notice that on average, it takes roughly, the colors are always the same. It doesn't matter if I look at dwarf galaxy or spiral galaxies of different spiral shapes, morphology, okay? So what we did is we combined all the data, and we tried to derive these time scales. And here you see this is a time in million years, and this is the mass of the star cluster. And now we count how many clusters there are in different phases. So when we go from embedded to partially embedded, we will see these are the square data, okay? And when we go from embedded to fully exposed are the circles. And what we find is that depends on the mass of the star cluster, these emerging timescales are different, okay? So what does it mean? Why is it so interesting? Essentially, it's telling that to form a rocky planet, you need quite some time, okay? You need at least 4 to 5 million years. So rocky planets cannot form easily in a massive star cluster. But they will form very likely in lower mass star cluster, okay? If you want to produce ionizing radiation to reionize the universe, you don't care about the low mass star cluster because they take forever to emerge from their dust. But the high mass one are fast and they clear their surrounding very quickly, okay? So this is an important result that we have, and here I put for those who know about the Milky Way, like what regions correspond like. So now I wanted to conclude this part and move to hierarchy with one more result, and it's about the fact that if we divide the metal rich and the metal poor, we see a significant hint that we are now following up with this cycle 5 JWST observation. And it's essentially that for low metallicity, the dusty embedded phase seems to be very, very short. And this is important even more for reionization, because the low metallicity galaxies are the analogs of the galaxy that have reionized the universe, okay? So we are doing a bit more on this. So we are now at 3:30. I will move into the second part. And we are going to look at the galaxies at higher redshift. So we are moving away from the local universe. And you have to think when we do that, we are going to lose even more details because the galaxy becomes much smaller, okay? We are looking farther in space and time. So to go back to this picture, we saw the blue spectrum is a star-forming region in a local galaxy. The effect of redshift is that this, we will see the emission from galaxies, the rest frame emission. So this is, I told you, was UV. Now it's moving into the optical, okay? And it's even more. So what happens is before we looked at the universe with JWST, we could only look at the UV rest frame of galaxies. But now with JWST, and sorry, one more slide. This is what we saw when we used the JWST. So at redshift 2, this is roughly about 4 gigayear after the Big Bang. Galaxy didn't look like galaxy in the local universe. So disks are not morphologically the same. It's not just a lack of resolution or resolving the details. They physically are different at redshift 2, okay? And then if we add now JWST, this image is going to be different again because we are not covering only the UV, but we get the optical rest frame. So we can see more of the components of galaxy as we move to higher and higher redshift. In particular, for this talk, we have to introduce the concept of gravitational lensing. So when you have a mass in space, it will bend space and time, right? And we use this as an instrument to actually resolve galaxies. So here you see you have a mass. It's a galaxy cluster. And this mass is bending the light of galaxies which are in the background. So effectively, this is now an JWST image. You see there is a lot of yellow light. This is a galaxy cluster. It's one of the most massive regions we can see in the local universe. And it's bending the light of galaxies that are a much higher redshift. So that's why galaxy here looks like arcs. You see all these red arcs? These are all redshift galaxies that are, they are like stretched in one direction because there is this mass in front of them. And then we can, with a model, reconstruct how the galaxy looks like and what is inside the galaxies. And this is really important. So when we do that, right, what we see is that galaxies, these are galaxies without lensing, without magnification. we see already some structure, but now we are not at redshift 2. Here we are at redshift 9. We are just 500 million years after the Big Bang. We see already the galaxy have disks and structure. They are not the point sources. And then when we have the lensing effect, so this is the resolution. When we have a lensing effect, this galaxy light is stretched. We can see more into the details of galaxies. And then depends how magnified they are. We can reach 100 parsec scale, or we can reach 1 parsec scale. And now if you see, these galaxies are very stretched. Sorry, the light here is not ideal. It's not because of the shape of the galaxy. It's like a spaghetti, right? That is the effect of magnification. It's magnified, stretched in one direction by gravity, okay? And we see all these little dots are the star cluster that we are looking in the local universe, but now in much younger galaxies. So if we look now at the highest redshift system we could resolve with the magnification lensing at JWST, we are here at redshift 11, 12, 300 million years after the Big Bang. Galaxies already look with structure, very dense, compact structure in them. And then we continue, we follow galaxy growing, and here we are 1 gigayear after the Big Bang. It's redshift 6 at the end of reionization. And we see the galaxy have a lot of these little dots there. Star cluster, these are the globular cluster forming. Probably we are seeing at the condition where a globular cluster formed. And if we wait long enough, now we are looking at cosmic noon. All these little dots around galaxy are a globular cluster in the halo, exactly as in our Milky Way. We see the globular cluster around our disk. And we see that, but at redshift 2. So the question we ask now is, are we witnessing the physical properties of galaxies where globular cluster formed? And to do that, I've tried to produce this plot. So let's break it down. There is a lot of data here. But anything which is plotted in black or gray or white with black contours, these are galaxies observed with JWST. And since we have a spectroscopy, we can determine their element abundance. For astronomers, this is the oxygen abundance, which then can be converted to a metal abundance of galaxies, okay? And here we see the galaxies in a sequence as less massive galaxies have less metals in them. And that's correct, right? You expect the lower mass galaxies have not yet polluted, produced enough elements to become rich like our Milky Way, okay? And these are really metal poor. And here you see some of the system are some of the most metal poor galaxies. Almost, it's like 1% of the metals that we see in our Milky Way. So these galaxies are really, really metal poor. And here, this is one of the, we call it POP3 candidates. Maybe it has some of these pristine stars with no elements in them. And then here in colors, I'm plotting now the globular cluster that we observe around the Milky Way, Andromeda, in our local group. And their metallicity, their abundance, are now on this side. The two axes are connected. And we see essentially that very likely the galaxy, the most metal-poor galaxy that we are gathering, are probably the places where the most metal-poor globular cluster are forming. Okay. Another aspect that we can now study, since we can look at star cluster at high redshift, and if we don't have enough resolution, we call them clumps, we can look at the star formation rate density. And now, star formation rate density is the ability of forming stars per unit time. And area. So take the same area, how many stars can you form? 1 million, 10 million, 10, right? This capability of forming different mass in stars tells us something about the condition of star formation in galaxies. And what we see now, I'm plotting here redshift bins, okay, is that as we move to higher redshift, it seems that these little dots, these little clumps, can form much more stars, a higher number of stars than objects that are at lower redshift. This is a two effects, okay? One, they are more compact and they form more stars per unit area. The other is that the universe at this redshift is much younger. So you will find preferentially objects that are forming stars now. So there are two effects in this plot. And the second plot that I want to show you today is about the stellar surface density. Do you remember at the beginning, the globular cluster had like this million stars, while the open cluster, which one did I show? The Pleiades had maybe a few hundreds of stars that are visible, okay? That is a quantity that can be measured because we have now the size and the mass of the object, and we call that quantity stellar density, okay? And here you see that in blue and reddish color, the star clusters are much denser than clumps, and we can understand them because star clusters are very compact, a few parsec in size, while these are regions of 100 parsec. But then we also see that there is this slow redshift evolution with both clumps and cluster becoming more compact as we look at higher redshift galaxies. This is again an interesting result. One, galaxies are more compact at high redshift. They are not as large as our Milky Way. Galaxy sizes are evolving and becoming more compact. And secondly, they are much denser. And to give you an example, this is the average density, this band, our average density of globular cluster around the Milky Way. And we are looking now at a young star cluster, a very high redshift, with density that are a factor of several denser than even globular cluster, okay? And this is really interesting now, because I told you at the beginning, the distance between the sun and the closest star, 1 parsec, you have 10 to the 6 stars, okay? Now if you have a density of 10 to the 6 solar masses per parsec, the number is much higher. So we reach now conditions which are really extreme. For instance, from 10 to the 3, stars start to merge in the center. And this is, we call them runaway collisions, is how you can make very massive stars of few hundred up to 1,000 solar masses, okay, in the center of star clusters. And then at this high density here, you can have runaway collisions between stars and even stellar black holes, right? And now, when you merge stellar black holes, you can grow these intermediate mass black holes, which becomes seeds for the supermassive black holes we see in the center of galaxies. Okay, so this is really interesting because then it connects to the history of how supermassive black hole formed. In this cartoon, you see you have a very high redshift, you have protogalaxies, and there are different channels, and one of these are this nuclear star cluster or merging of black hole in star cluster. There you can create the seeds for supermassive black hole at low redshift. Okay, I'm at the end of my talk. I've been talking now for 45 minutes. And just to give you a quick summary, we looked at the local universe with JWST, and we see that emerging timescales depend on the cluster mass, and very likely also on the metallicity. And this is a property that we are going to explore in the next few years. And then as we look at the redshift universe, we see probably the places where globular clusters form, okay? We can look at their condition. They formed in very dense, highly star-forming galaxies, and possibly they are also the seeds for intermediate mass black holes in the early universe. And that's it. Thank you very much.
So thank you, Angela, for the nice talk. I think we have time for some questions. So if there is any question.
It's a curiosity, I mean, and not a very probably important question. The embedded star cluster under dust, etc. What is the ratio of mass between all these, let's say, not luminous? It is also, let's say, absorbing. And what is the mass of the stars inside?
Yes.
That's a curiosity.
Yeah, it's
probably
called,
the answer is it depends, of course.
It's called the star formation efficiency. So essentially, when the stars start to form, right, it's 1 to 0, 1 gas, 0. At the end of the process, I would say that it could be between 30 to 80% of the gas has become stars. It depends on the condition under which stars are forming. And the gas...
Because of
yes, that's what happens when you look most likely at low star-forming regions, so the one that form 10 to the 3 solar masses. But when you look at very massive star-forming cluster, I think the efficiency there is higher. So you remove maybe 30% of the gas will be missed, but the free fall time for very dense region is short. So it will go very fast, and most of the gas will be in the stars.
I have a second question, which is technical. The lensing of a gravitational, let's say, point, like,
yes.
Like you said, cluster of something massive, allow us to see faint things and strip it all around. I don't know if you said that it is possible to reconstruct the exact shape of it. Is it...
we can, the exact...
I mean, it depends how much you can reconstruct by this,
we can
let's say,
reconstruct them
to the real...
For a system like this one I was showing in the slide, let me go back to it. We think it's quite relaxed, this cluster. You see, the light is quite, then we can reconstruct very well the lens model, and then we can go back to the shape of galaxies. But there are other galaxies where the model, the lensing model, is not known so well, and then there the characterization.
So the limitation is to know what is the let's say, the massive object that gives you, okay. But in principle, it is possible to,
yes.
to reconstruct as a
yes.
powerful tool to look further. I mean,
yes, it's like a magnification glass. So if your glass behaves well, it's easier to correct for it. Yeah.
Thank you.
Thank you. Good afternoon. I I'm actually a little bit curious about you explained about metal poor cluster that has embed to the starless phase, to young cluster, to young star cluster. So I think it's very interesting because from the lecture of Professor Milano, we talk about a lot about the metal poor cluster, but my question is actually about if there's the case of we have the metal poor cluster that embed the phase, like from the previous slides. I think previous again. Sorry.
This one.
Yeah, the thing, the embed phase of the star from the starless phase to the young star cluster. So you said that it's because the metal poor clusters is very embed to that class, to that thing, to that phase of the starless to the young star cluster. But my question is that if there's the case that actually enough time for a second generation of the emerging sequence star formation from the starless phase to the young star cluster, is there any change for the form of another star formation after this phase because of the metal poor clusters that happen?
So the answer to your question is we don't know, right? Because it's not clear what is forming the enriched population in globular cluster. And also the other answer is we are looking at the local universe and the pressure in the disk, the condition for star formation, even in dwarf galaxy, that we call them analogs of high redshift, are exactly not the same. So the time scale that we are seeing are indicative for the local universe, but actually we don't know how long things stay embedded at high redshift because the gas pressure is higher, so it will take more work to blow the H2 region and remove the gas. So the time scale cannot be transferred one-to-one. So the short time scale for the dust to be destroyed at low metallicity, I couldn't give you all the details, but we want to understand the two different effects. So why this is so short here, okay, with respect to the spirals. I think, so the problem, it could be that the dust is not forming PAH. So the molecules that create this emission are actually not forming because the UV radiation destroys them very fast, okay? Or the other is that, yes, the UV radiation is too fast and is destroying. So there are two competing effects. One is that the formation of PAH is different at low metallicity, which is plausible. We see variation. And the second is that the UV radiation is harder at low metallicity and destroys them more rapidly. But this is, again, an image for something that is in the local universe, and we cannot transfer one-to-one at high redshift. So we are trying, yeah, we do what we can to learn, and one simulation can produce what we see in the local universe. Then we can apply the same physical processes with different ingredients at high redshift.
So we cannot use another this technique to another kind
of? At high redshift, no, because at high redshift, if you remember, JWST is giving us only the optical now. We miss the infrared that we need for doing these studies. That's, yeah.
Thank you very much.
We need to build a big more telescope. Give us money.
Thank you. And first of all, I have a little question about the graph, about the data from the local group galaxies and the higher redshift galaxies. And my question was, the first thing that occurs to me in that graph, probably in some later slide, was the big difference in masses. And like I was thinking about it, and I was asking to myself if this can be explained exactly just by the ionizing process or something else.
I forgot to say it more clearly. So these are a galaxy, right? And their masses are already quite low because we are reaching really the very low mass end. And these are globular class. So these are like stellar objects, right? They formed inside the galaxy. So if they would be more as massive as the galaxy, then something is wrong, right? So this is like a fraction of the stellar mass of these galaxies is inside each of these objects. And that's why the mass is so different, okay? Did I answer your question? Yeah.
So any other question?
Yes, I had a question on the last couple of graphs. And I didn't quite catch how the two different classes of clusters and clumps are defined across the different redshift bins.
Yeah. So as you know, we have a really hard time to resolve, right? Because it depends on magnification. So we arbitrarily decided that structure which have a 20 parsec or lower sizes, we call them star cluster. And structure with 20 parsec and above can be hundreds parsec in size. We call them clumps. And most of the clumps are a structure we don't resolve enough to see the star cluster within them.
Okay, thank you.
Thank you for your question.
Okay, any other question? Okay, so if there is no other question, let's thank the speaker again. And yeah, Angela will be around today and tomorrow. So if you want to chat with her, she will be around. She has the office in Vicolo dell'Osservatorio. Thank you, and see you at the next colloquium.